Hey guys, welcome back to paper 2021, paper 1 for chemistry this time. So some of you guys really enjoyed the biology one, so I'm going to do one for chemistry as well, and then we'll do a physics one sometime during the next week at some point. Chemistry can be very annoying because you have to remember a bunch of different stuff, which is not the easiest thing in the world. And in fact, question 1 gets straight into the remembering the annoying stuff. So this question's about metals and non-metals, and we have an outline of part of a periodic table. So we have things like the hydrogen and lithium and all of those kind of gases on the side. We have the transition metals. We have some more metals over here. And then we have part D. So we have element Q is a dull solid with a melting point of 44 degrees. Element Q does not conduct electricity. So what we want to do is label the 3 bits of information. Well, maybe 4. So we have the fact that it's dull, it's a solid, and it's a melting point of 44 degrees, and it does not conduct electricity. And that will help us eliminate sections of this diagram because we are trying to work out what section is most likely to contain Q. Now, if I look at a few of these things, dull means it's not shiny, which means it's probably not a metal, because metals in general can be polished, which means they can become shiny. The same thing with this not conducting electricity. I know that not all metals conduct electricity, but generally speaking, metals do conduct electricity. So the fact that it's dull and it does not conduct electricity eliminates metals, which means we're eliminating the transition metals and these groups of materials over here. So we have like aluminium and germanium and things like that, which are metals as well. But B is the transition metals. We could definitely get rid of that. Okay. So now we have that it's a solid with a melting point of 44 degrees Celsius. So generally speaking, as we go down a table, generally speaking, the melting point will increase. So for example, all the way up here, you have things like hydrogen and you have helium over here, for example. So those two are gases at room temperature. The liquids are towards the middle, and then most of the table is actually a solid. For B and C, they're all solids, but we've already gotten rid of those because we know that they're not metals. So with A, because we have a lot of kind of gases and liquids on this side, it's actually going to be D, which is the one that's most likely to contain Q, because everything here besides the helium is actually a solid at room temperature. So that is, and again, that's why the melting point being 44 degrees, room temperature is about 20-ish degrees is what you're kind of thinking of. That is where my logic and my understanding comes from. We should also keep in mind that on the left-hand side of any periodic table, when you have things like sodium and you have these kind of ionic compounds, elements, they can technically conduct electricity. So sodium, if you dissolve it in water, can, for example. So that would be the reasoning for it being D. This one is a little bit cheeky. So element R forms ions of formula R2+ and 3+. So which section of the periodic table is most likely to contain R? If you remember, the way that we form ions in chemistry is the loss of electrons. So generally speaking, you're looking at so for example, group A. So let's look at group 1 and group 2, for example. Because they have 1 or 2 electrons in their outer shell, they will always lose electrons, right? Which means they'll form ions of either 1+ or 2+. Now, here is the kind of key thing that we need to think about, is the left-hand side of the table goes up to group 3, and then we have a bunch of these middle ions, and then we have the ones on the right. Now, the ones on the right, so we're thinking of anything above group 4, really. So group 5, 6, 7, and 8, for example, so the noble gases. Technically, the noble gases won't react at all, but these elements here in group 5, 6, and 7, they will always gain electrons, which means they will always form ions which are negative because they're gaining electrons. Electrons are negative, so they're gaining negativity, which means they're going to become more negative. So we know it's going to be on the left-hand side somewhere. So either A or B is what I'm thinking, okay? Because it can't be D because those are the group 5, 6, 7, and 8. 8s won't form any ions whatsoever because they are stable. 5, 6, 7 will always try and gain electrons so they become negative. Now, here's the interesting thing, is that it can form different ions. So group 1 elements will always form +1 ions. Group 2 will always form +2. So it's not actually group A. Instead, you're actually looking at the group B materials. And that's because they are the transition metals. They behave differently to the other groups. That's why you have a gap. So it goes 1, 2, 3, 4, 5, 6, 7, 8, right, in your periodic table if you were to get it out right now. the middle, the transition metals behave differently. And one of those differences is that they can form ions of differing charges. So what do I mean by that? So it could be 1 plus, 2 plus, or 3 plus. So that's why it's most likely to be in group B. Because group A, they will only form certain ions. So that would be my reasoning for part 2. Give 2 differences between the physical properties of the elements in group 1 and those of the transition elements. So this is a really good question, and it's a very common one. Now, if you look at the transition elements in the middle, they are all metals. So think about the difference between the non-metals and the metals. So when we look at the non-metals, think of a few examples that we have. So you have hydrogen, lithium, sodium, magnesium, etc. Have a think about those and what kind of properties they have. In general, again, we're looking at group 1 actually, so I did say magnesium, which isn't group 1, that's group 2. Cesium as well, for example. Again, you do have a periodic table in front of you in the chemistry exam, so don't worry too much. But in terms of the differences, there's more than 2, so I will write all of them, but you only need 2 of these. The first one, if you again compare it to metals, is that they have, the group 1 elements have lower melting / boiling points. And again, if you take the most extreme example, hydrogen is in group 1 and it's a gas, which means its boiling point is below room temperature. There is no metal that is a gas at room temperature, which means they must have a much higher melting or boiling point. In fact, in general, melting or boiling group 1 metals is easier than all of the transition metals altogether. So that's one thing you can say. They have lower densities. So generally speaking, the metals are a lot heavier than group 1 elements. Again, that should hopefully make sense. Hydrogen floats in the air, for example. Lower density, they are less strong. Again, if you think about metal is generally speaking quite hard and solid, whereas something like cesium or even sodium, you can actually break apart in your hands. Nice and easy. And less strong is similar to also softer. So those are the 4 main ones. However, there are a couple that were in addition, which is they are more malleable or ductile. Because that relates to the whole softer / less strong thing. Because if you can manipulate them, it means they must be softer. You can also say not useful as catalysts. That's one that I haven't really seen any students write before, but it is one that was remarked as being present in the 2022 paper, which is kind of interesting. Obviously, you can say the exact opposite, right? You could say transition elements have higher melting and boiling points, higher density, more strong, soft and harder. So you can say the exact opposite, of course. It just depends. I've gone with group 1 elements are lower and whatever. So for part 4, we have to draw the electronic structure of an aluminium atom. This is a question I can practically guarantee will come up this year. They will ask you to draw a structure of any kind of atom, and it does say use the periodic table. So what I've done is I've copied one over. This isn't the exact same one as the one you get in the formula booklet, but it is basically the same thing. So what do you want to look at when you're drawing an atom? A good thing to look at is the group that the atom is in and something called the period that it's in. So the group is simply how far left and right it is. Now, unfortunately with this one, because it's online, is a bit wonky, but again, you are basically ignoring this middle section. So it's group 1, 2, and then your one will say group 3. So if I cross these out, that's what your one will actually say. Okay, so we can ignore all of these. So first of all, finding aluminium. Aluminium is right over here. So Al, it's 13. So the group is 1, 2, 3. So what does that mean? Well, the group of 3 means that there are going to be 3 electrons in its outer shell. So 3 electrons outer shell. Now, the period will tell me how many shells it has. So, in this case, the period is 1, 2, 3. So if you like, it's almost like coordinates in maths. It's 3 across, because there's a 3 here, and it's 3 down. So what does that mean? Period 3 means that it has 3 shells in total. That's all it means. And now you can fill it in. Now, I know that some people will also say, well, you look at this number as well, and that tells you how many electrons it has in total. That's totally fine. I've never never bothered with that because this actually tells you all the information you need. There are 3 shells, and the last shell has 3 electrons. That's it. The only thing you need to remember now is that the innermost shell always has 2 electrons at the most, and the rest will have 8. So that's 1 shell done. The second shell is going to be full because, again, there's 3 shells in total, so the first 2 have to be full. So you'd pair them up like so, draw them 90 degrees apart like this. It does make a difference, you do need to have them spread out. And then it tells me that there's 3 electrons in the outer shell. So 1, 2, 3. That's it. If you add these up, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, I have 13 electrons as well. So that's why this number here is a bit redundant. You don't need it if you're sketching a electronic structure. The group 3 tells me there's only 3 in the outer shell, and the period 3 tells me there's 3 shells in total. So the first 2 have to be completely filled because they fill from the middle out. If there's 3 shells, that means there's 3 shells with electrons, so the first 2 have to be full before you go on to the third one. And the third one has 3 electrons. That's literally it. That's all you really need to care about in this case. So hopefully that helps a little bit in terms of using the periodic table. Find the group, find the period, and you can sketch any atom. I would recommend practicing this. This is a really good 3 marker. So aluminium is a metal. Describe how metals conduct electricity, answer in terms of electrons. This is something you can pretty much just memorize. But the idea is I'm going to explain the logic and then I'm going to give you the 3 points. Because remember, I'm a big fan of bullet pointing. So we're only going to have 3 bullet points. Okay? 3 marks, 3 bullet points. Essentially, when you have a metal, normally in materials, the electrons are stuck to their atoms. They don't move. So something like wood or carbon or anything like this, their electrons are stuck to their atoms and they can't move. Now, electricity is just the movement of electrons. So if no electrons are moving, there's no electricity. That's why something like your table or a plastic bottle, for example, will not conduct electricity because the electrons are stuck to the atoms. They can't move even if they wanted to. So no electrons can move through it, therefore no electricity. Metals, on the other hand, their atoms, on the surface especially, their electrons are not joined to their atoms. So their electrons are free to move around and go wherever they want. Now, because we can move the electrons, it means electrons can move through the material, which means movement of electrons, what is that? It's electricity. So whenever electrons can move, that is electricity. That's all electricity is. So, what do we say when the electrons can move from their atoms? We say that they are delocalized. Now, that word sounds really fancy, but let me explain it. If something is localized, well, what does it mean when something's local? Local means that it's near to you, right? So when you've localized something, it means you've put it in a certain place. So delocalized means that it's not attached to a certain place. Localized, it's in a certain place. Delocalized, it's not in a certain place. So this little phrase here, which you've heard a million times before, literally means that the electrons do not have a fixed place, i.e. they can move. So, the electrons, how you kind of talk about this is different, but the electrons can carry electrical charge through the material or the metal or whatever you want to say, through the metal. So again, because we have electrons that move, that means they can carry the electricity through the metal. That's all we're saying here. Not that bad, hopefully. This right here is a bit of a memory game. It might be good to do like a little matching exercise or something like that, but remember from the biology video, flashcards work wonders with the things you don't know. So if this 3 marker you're okay with, don't do a flashcard on it. Why would you look over something you're okay with? That's pointless. You're wasting time. Be efficient so you don't have to study as much, okay? Because there is a limit to how much you can study. So, metals and non-metals. Well, let's go through all of the possibilities, right? You either have non and non. You either have non and metal. And you have metal and metal. Those are the 3 possibilities, right? Now, it is a bit of a memory game. However, one of them I think is quite easy. Metal and metal has metallic bonding. So metallic is literally just the adjective describing a metal. So the bonding between metals is metal-y. It's metallic. Okay, cool. Non and non, that is where you're going to be sharing electrons, so that is covalent. And therefore, non-metal and metal will be ionic because you have a sharing, you have a taking and losing of electrons, a gaining and losing of electrons. Again, that is a bit of a memory exercise. There's not much you can do to memorize it. However, I think metallic is generally speaking fairly easy for people to remember because it's metal and metal is metallic. Okay, cool. So it's a 50-50 shot, basically. Magnesium oxide is a compound formed from the metal magnesium and the non-metal oxygen. So they've told you now that it's ionic bonding. Describe what happens when a magnesium atom reacts with an oxygen atom in terms of electrons. So this is really good because they've low-key told us it's ionic. So we know that one of them is going to lose electrons, the other one's going to gain electrons. So 4 marks, let's think of what the 4 points would be. Well, what we're going to have to say is which atom will lose electrons. Then we're going to have to say which atom will gain electrons. Okay, so that's the kind of idea we're looking at here. We do not want... Anyways, let me space those out a bit more. So again, we want to write what atom loses electrons, which atom gains. That's 2 marks. Then how many are gained or lost? That's the 3rd one. Now, what's the 4th mark? The 4th mark is what people usually forget. So let's start with the first 3 marks, okay? So, describe what happens when a magnesium atom reacts with an oxygen atom. Let's find out quickly where they are. So magnesium is here, Mg, so it's in group 2, and oxygen is in group 6. Now you might wonder how I found the oxygen quite quickly. A, it's practice, but B, the most important one, is that if I know magnesium's group 2, that means it has to react with something from group 6, because there has to be full outer shells at the end. Sorry about that, I had my doorbell ringing a bunch. So anyways, magnesium is in group 2, and oxygen is group 6. Now, just as a reminder, anything below group 4, so 4 to the left, will always lose electrons. Anything, I don't know why I'm writing them before again, don't need to. Anything to the right will always gain electrons. Because remember, they always do the easiest thing. It will be easier to lose less than 3 electrons, so 3 or fewer electrons, than it is to gain 5 or more. So for example, with group 2, they're not going to gain 6, they're going to lose 2. It's way easier. So what happens in group 4? Well, normally they just do covalent, so they share, but they effectively don't really care. So they could lose, they could gain, because it's equally as challenging either way. So, in this case, oxygen will lose, magnesium will gain. That's what we need to do. Mg gains electrons, O loses electrons. And then I'll just write how many. Well, again, magnesium is in group 2, so in its outer shell it only has 2 electrons. So it can only lose 2 electrons, which is really useful because oxygen has 6, and it would really like 8. And what is 6 plus 2? It is 8. So, 2 electrons are transferred. I would recommend, so in terms of me writing E minus, for example, that is normally accepted, but you can write out fully as like electrons. That would probably be the best thing. In terms of group 8, by the way, they don't really do anything. So they don't really react at all. So what was this last thing that I mentioned? And this is the mark that is often overlooked. These first 3 marks, people are, not bad, not bad. What about the last one? Well, it's the special thing that is only, it's only to do with ionic bonding, which is ions are formed. So magnesium and oxygen ions are formed. That is the only other thing that you need to write for those 4 marks. So in total, I mean, how many words is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 words, 4 marks. It's a pretty good ratio right there. So these 6 markers are often quite interesting. And well, let's read through the question first. So sodium carbonate reacts with hydrochloric acid in an exothermic reaction. Remember, exo means outside, and thermic is anything to do with heat. So this literally just means outside heat. So it heats up the surroundings. It gives off heat. The equation for this reaction is the sodium carbonate plus the hydrochloric acid gives you sodium chloride plus carbon dioxide plus water. A student investigated the effects of changing the mass on the highest temperature reached. Plan a method to investigate the effect of changing the mass of sodium carbonate powder on the highest temperature reached. So, in terms of how you do this, a lot of students think that you need to write paragraphs because, I'm just going to read from the mark scheme really quickly. Level 3, the 5 to 6 marks, the method would lead to the production of a valid outcome. The key steps are identified and logically sequenced. What does that mean? Logically sequenced means you do it in order. So for example, I wouldn't say, mix the sodium carbonate with hydrochloric acid. Put the hydrochloric acid in a polystyrene cup. Like, you'd put the hydrochloric acid in the cup first, then you would put the sodium carbonate, sorry. You know? So you need to make sure that you're not contradicting yourself and that you're doing things in order. So the best thing to do is A, have these investigations already pre-planned, right? You know what it kind of, in your spec, there is a set of required practicals that you have to know. So practicing these questions, you can literally just have a 6 marker in your head already, right? No harm in doing that. However, let's kind of go through it. So, and this will help you if you want to do A-level biochem or physics as well, by the way. When you're planning an investigation, the things that you really need to be aware of is what is your independent variable and your dependent variable. Those are the two really key things. Now, the dependent variable is the thing you're going to measure, and the independent variable is the thing that you're changing. So investigating the effect of changing the mass on the highest temperature reached. Now, I'm not changing the highest temperature. That's happening automatically. But I am changing the mass of sodium carbonate. So it's the mass of the thing. The dependent variable, the thing that I'm going to measure, is the temperature. And then all you need to do is think about how you measure those things. So temperature, that's fairly easy. It's a thermometer, right? But you have to be careful because when you're measuring the highest temperature reached, you need to take into account the starting temperature. Okay? Because if I do this in the winter versus in the summer, the hydrochloric acid is going to start at a different temperature. If it's 0 degrees in the room, then hydrochloric acid will be at 0 degrees. If it's in the middle of summer, it's 20 degrees in the room, the hydrochloric acid will be at 20. So it's not fair to compare those two temperatures. So we have to take into account the starting temperature. We're looking at the difference in temperature. So let's go through exactly what we need to do. We also need to think about ways that we can minimize kind of variables that we don't have much control over. So again, the temperature could be a good one. So don't do it over the space of a few days. Like you want the weather conditions to be the same. As an example, you want to use the same amount of hydrochloric acid because we're changing the mass of sodium carbonate, not of the hydrochloric acid. Okay, so those are key things. How are you going to stop heat from escaping? Are you going to put a plastic lid on top of whatever you're doing so you can make sure that the heat doesn't escape? All of those different things. So, again, you can use bullet points. If you teach, so yeah, anyways, I'm not going to talk smack about teachers, but again, bullet points are completely fine. In fact, if you look at the mark scheme right now, it's in bullet points. So yeah. Anyways, what do you want to do? Well, you want the amount of hydrochloric acid to stay the same. So I'm going to say measure a volume of hydrochloric acid. Actually, it's not capital L. That was Freudian slip there. And how would you measure it? So whenever you talk about measuring something, how do you measure it? Measure volume. How? Well, using measuring cylinder. There you go. Boom. 1 mark. Cool. What else do we need to measure? Or what do we need to do? Well, what are we going to mix the sodium carbonate and hydrochloric acid in? Well, some kind of cup would be a good idea. Again, bear in mind it's acid. So you want something that can withstand acid. So a plastic container, a polystyrene cup. Polystyrene is plastic, so I didn't really need to specify that. But whatever. At school, you probably used a polystyrene cup. Probably. Pour HCl into polystyrene cup. Polystyrene cup. Measure the initial temperature. Again, we need to take into account the initial temperature. Initial temperature using a thermometer. What kind of thermometer? You don't really need to specify because both are fine. Digital is technically better than an analog one. The analog one being the thing where you measure, you look at how high the red bar goes. Digital is technically better. It's more accurate, more precise. Sorry, not accurate. That's good so far. So we've got 3 marks so far. Now we're actually talking about mixing the actual sodium carbonate. It was sodium carbonate, right? Yes. Mix. And here's the key thing. Don't just say mix sodium carbonate. Mix a known mass of NaCO3. I'm trying to think of a short way to write this. With hydrochloric acid. It would be a good idea to stir. So when it says mix, it's a good idea to say like to stir it as well, because that can impact your results. We also known mass measured with balance. By the way, you know the way I'm writing it now, with the arrows coming off, that's completely fine as well. So that's pretty good too. I'm going to get rid of that bullet point because we've got different things there. And measure highest temperature recorded. Highest, T recorded. Again, using thermometer if needed. So far we've got 1, 2, 3, 4, 5 marks. What's the last mark? Well, let's look back at the investigation. The effect of changing the mass of sodium carbonate. I haven't changed the mass yet. So now I would say repeat with different masses of NaCO3, and that would give me the full 6 marks in relatively few words. Relatively few. I know it's not like the most concise thing, but hey, you know, what can you do? In terms of some other things you can say, you can mention things like using the same starting temperature, volume of HCl, and concentration, but we've already kind of mentioned that by saying that it's a known mass, for example. But you can add those things if you want to. So here we have a line of best that fit through the students' results, and it says that we need to determine the gradient for 5 marks and give the unit. This is why I love GCSE science. These calculations, just like in the biology exam, are so good. They're not super easy, but you get so many marks for something that's relatively short. So it says, it gives us the equation, which is even better. Change in the highest temperature over the change in mass. So all you're doing is how do you work out the gradient in maths, right? You're doing the same thing. You're working the difference out in the temperature and the difference in the mass. That's all you're doing. So it is literally just the equation we use in maths. So change in mass is probably the easiest one. It starts off at 1 and goes up to 5. So if you want to be really specific, you can write 5.0 minus 1.0, or you can just do 4, but whatever. Change in highest temperature, well, it starts off at what? Well, it goes up in what looks like 0.2s. How do you work that out? Well, if you look, the difference between these two things, 24 and 22, is 2. And how many spaces are between them? Well, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it must go up in 2 divided by 10, 0.2 marks. So it starts off at 22.2 and it ends up at 28.2.4.6. So 28.6. So we're taking the difference of those two numbers as well. 28.6 take away 22.4, 22.2. Okay. There you go. We get 4 marks for putting this into a calculator. I love science. In terms of an exam, really, really good. And 5. Again, I'm entering it exactly. You don't have to, obviously. Just double checking. Cool. 8 over 5, so that's 1.6. And that gives us 4 marks. So the 5th mark is for the unit. Now, the unit is something that is tricky. So all you do is, what would the unit of temperature be? Well, if we go back up here, it tells me it's in degrees Celsius. So we've got degrees Celsius here, yeah? What's the unit of mass? So this could be a few different things. It could be kg. It could be, in this case, grams, which makes sense because, I mean, I'm pretty sure none of you in your experiments at school use kilograms of stuff. because that would be quite interesting. And we're dividing, right? So we have degrees Celsius over grams. We'll just write that. Degrees Celsius over grams. That's it. That's all you have to do. To work out the units, you literally just write the units of what you've used, so temperature and mass. And if you're dividing, well, you just put a slash between them. If you're not dividing, well, then you put them just next to each other. That's it. Not too bad. And that is 5 marks. Pretty good. By the way, if you wrote degrees Celsius per grams or per gram, that is all totally fine as well. The initial temperature of the reaction mixture is where the line of best fit would meet the y-axis. We need to determine that with 2 marks. And it says show you working on figure 3. There are 2 ways to do this. One is using the gradient. I just realized I should have written this up here. One is using the gradient we just worked out. The other way is simply by continuing the line of best fit. So, I mean, I would probably I'll get my ruler and I'll draw a line like this. That's not bad. Something like that. So that's 20.24. I'm going to say 20.6 if you continue that a little bit, which is actually the right answer, which is amazing. But what they're looking for is you get 1 mark for the answer. You get 1 mark for actually continuing the line of best fit. Again, use your ruler and line it up. The other thing that they're looking for that you could have done is using the gradient. So if you notice, it starts off at 22.2 at 1 gram. So at 0 grams, you would just have to take away another 1.6, which would give you 20.6 as well. So either one of those would work fine. Another student repeated the investigation but added sodium carbonate up until sodium carbonate was in excess. So what that means, whenever you hit the word in excess, is that eventually not all of it reacted, is the idea. That's the idea, that's in layman's terms. What does it mean scientifically? Well, it means that it's no longer the limiting factor. So they've put in so much that there is too much sodium carbonate that will react. So it's not the thing limiting the rate of reaction. Remember, this highest temperature thing it's to do with the rate of reaction. Eventually there won't be enough acid to react with the sodium carbonate. That's what they mean by in excess. So which graph shows that? Well, this is really weird. The mass of sodium carbonate goes up normally, which is what we expect, and then it peaks somehow. Okay? The next one is it just goes up forever, just like our previous one. That doesn't show in excess. Because again, they haven't kept adding more and more sodium carbonate until the rate of reaction no longer changes. Instead, you would get something that looks like graph C. This is true even for photosynthesis in biology, by the way. Anytime you have a limiting factor, eventually what happens is the rate of reaction plateaus because the thing you're changing is no longer the thing limiting it. So in this case, we've added so much sodium carbonate, there's actually not enough hydrochloric acid to react with it. It's like if you tried to dissolve salt in water. I don't know if you've ever done this to get rid of ulcers in your mouth or whatever, but if you continuously add more and more salt, eventually the salt will no longer dissolve. As in, it will just build up at the bottom because there's not enough water to dissolve all the salt. Same thing happens with any other kind of chemical reaction. In this case, there's not enough hydrochloric acid to react with the sodium carbonate, so the highest temperature no longer changes. And it never will, because not all of the sodium carbonate is reacting. So it wouldn't be like this because that's not in excess, that's just a normal reaction. This is just weird. The mass, it should be linear, unless again it goes into excess. So do keep that in mind. We're going to do the next 2 parts together because they basically follow the same kind of style. So this is a reaction profile for sodium carbonate with hydrochloric acid. Remember that this was an exothermic reaction. It tells you at the beginning of the question. We have the reactants, it spikes and then it goes down and there's a lower something because we have to say what the something is. So what do X and Y represent? X is simply energy. Now this should make sense, right? Because the starting energy should be higher than the ending energy because we've released energy. It's exothermic. So energy has left the system, has left the chemicals in this case, in which case we're at a lower energy at the end. If it was the other way round, so if you flip this over, it would be endothermic because it's taken in energy from the surroundings. So what does Y represent? Energy change, or change in energy, overall energy change, whatever. Basically, energy change is all you need. And I've kind of answered the next part. How does the reaction profile show that it's exothermic? Because the product's energy is lower than the reactant's energy. Product's energy lower, that looks like I wrote lower than reactant's energy. And again, hopefully that makes sense, because that energy has to go somewhere, and in this case it's gone to our surroundings. And that brings us to the end of question 2. So this is all about carbon. What an interesting topic. No, I'm kidding. So here we have the representation of the structure of diamond, which is something you need to be able to draw as well, which is a bit tricky. Again, you don't need to be an artist or anything, but we need to describe the structure and bonding. So it's really good that they add this now, because it clears up any ambiguity. So in terms of the structure and bonding, again, we have 3 marks. I'm going to put 3 bullet points. There's only a few things you need to say. One is the type of structure it is. So it is called a giant structure. You can also say that it is as soon as I finish writing this word anyway, you can also say that it's macromolecular. You can say it's a giant lattice. Those are completely fine. Now, in terms of bonding, there is covalent bonding. And what's special about it? Because, I mean, pretty much anything to do with carbon is going to have covalent bonds. What's special? The special thing, the reason why diamond is so damn hard, is because it's bonding to the maximum number of carbon atoms. It's bonded to 4 bonds per carbon atom. So 4 bonds per atom. So each carbon atom is bonded to 4 other carbon atoms, which means it's the maximum number of bonds. That's why it's so damn strong. Similar to that, again, another 3-mark question. So we've already gone through 6 marks in this question already, which is really, really good, because it means there's not that many parts. Why does it have a very high melting point? So funnily enough, high melting points and strengths, when I said strong, actually very, very similar. So which is quite funny actually. So realistically, this could also be explain why diamond is very strong, and you can write the exact same points because they're due to the same thing. It's due to the 4 bonds per atom. So what happens when something melts? Well, you need to break the strong bonds between atoms so that way they can flow over each other. That's what a liquid is. So here are the points you need to write. Covalent bonds, or you can just write bonds, by the way. So bonds are strong. And bonds must be broken in order to melt. Be broken. So you have really strong bonds and there's lots of them and you need to break them. Well, that means you need a lot of energy to break them. So lots of energy required to break. Lots of energy needed to break. And that is a very important thing. So this energy can come from anywhere. That's why the strength is high. So you can either get the energy by hitting it in terms of strength, so that's kinetic energy, or it could be thermal energy, which is where you would melt it. So it is essentially the same thing. So if they ask you why they're very strong, it's because the bonds are strong, bonds must be broken, lots of energy needed. Why does it have a high melting point? Because the bonds are strong, the bonds must be broken, lots of energy needed. It's just one's thermal energy and one's kinetic energy. Here's another structure of carbon that you're expected to know. So this is called C70 and it's in these big hexagonal ball-shaped thing. So I'm going to go through some of the other ones. So graphene is a sheet, right? So it's these flat sheets of paper, almost, but of course made out of graphene instead. Nanotubes are tubes. So we know it's neither of those things. So we know it's not this, we know it's not this, because this is not a sheet and this is not a tube either. So it can only either be a polymer or a fullerene. That can help. Polymers tend to be to do with hydrocarbons, whereas in this case we literally only have carbon, so that means it must be a fullerene. But in general, fullerenes are just hollow balls, which we use in the medical field. And let's just do the next part as well. Molecules such as C70 can be used in medicine, so again, as I mentioned, to move drugs around the body. Basically, the drug sits in the middle of this big ball, and the fullerene ball goes to wherever it's needed, dissolves, and then the medicine is applied. It's just one reason why it's suitable for this use. Well, there is a million reasons. One is that it's hollow. I like this one because it makes the most sense, right? Imagine if I asked you to move a bunch of water from point A to point B. Well, would you want something that's a tube? Probably not. Would you want something that's a sheet? Probably not. Would you want something that's like a diamond shape? Probably not. Instead, you'd want something hollow like a bucket. And that's how fullerenes behave. They behave like buckets that carry medicine to where they need to be. So that, in my opinion, makes the most sense. But let's think about some other reasons. So the other reasons you could have given, I'm going to put them on the other side. It's unreactive because it's made of carbon. Remember, carbon's in group 4, so it's not very reactive. It's not toxic. So human beings are actually made up of lots of carbon. So, yep, completely fine if we have carbon in our body. It has a large surface area to volume. Large SA to V ratio, which means you can get this high rate of reaction between the medicine and the cells or whatever you're trying to deposit in the body. But hollow, in my opinion, makes the most sense. Calculate the number of C70 molecules that can be made from 1 mole of carbon atoms. Okie doke. So remember what a mole is. A mole is a certain quantity of a certain type of atom. So when we come across something like this, so what we have is 1 mole of carbon atoms. So that's not 1 mole of the C70 molecules. Now, how many moles of C70 would we have? Well, what we would do, moles of C70, is we would take the 1 mole that we have of carbon atoms and we would divide it by 70. Why? Because think about it. We would have 70 times less molecules of the carbon 70 because it's been joined together into these fullerene molecules. So if this was 2 moles of carbon atoms, you would change this number to a 2. If it was 3 moles of carbon atoms, it would be 3. Because again, the moles of C70 would be 70 times less than it. And then in order to work out the number of molecules, so number of molecules of C70, all you do is you take the number of moles and you times it by Avogadro's constant, because that is the number of molecules per mole. And that would give you your answer. 3 marks is pretty good. Not too bad at all. So just get our calculators out. 1 over 70. Well, again, really? Alright, times 6.02. Whoops, 6.02 times 10 to the power of 23. Gives me 8.6 times 10 to the 21 molecules. 8.6 times 10 to the power of 21. Job done. Next question is all about zinc and compounds of zinc. So a student produces pure crystals of zinc chloride by reacting zinc oxide with hydrochloric acid, so a classic displacement reaction. So we have zinc oxide, 2 moles of hydrochloric acid, makes zinc chloride and water. The student adds a zinc oxide to hydrochloric acid until the zinc oxide is in excess. Give one observation that the student could make to show that zinc oxide is in excess. So if you remember before, when I said in excess, it means there's going to be too much of it to actually react. So what that means is that there'll be too much zinc oxide to actually react with the hydrochloric acid, which means you are going to get lumps of zinc oxide inside this reaction. When you see that, you're going to have too much. Again, go back to the water and salt example. Keep pouring salt into water and eventually you'll get a pile of salt in the bottom of the water because the salt is in excess. It can't dissolve. So what you'd see, and again the reason why I know it's a solid is because it's S for zinc oxide. S means solid. Aqueous means normally it means it's dissolved in, for example, and L is of course a liquid. So simply there's going to be a solid remaining. So you could call it a residue, you could say lumps, you could say anything that implies there's some solid bits left over. Yeah, that'd be it. So point 2, why is excess zinc oxide used rather than excess hydrochloric acid? And the reason for this is, think about after the reaction, you'll want to kind of purify the crystals, right? It's easy to separate zinc oxide. It's not so easy to separate the hydrochloric acid because it's very hard to filter that off. So simply put, the zinc oxide can be filtered out because it's a solid. Generally speaking, you want to always, if you can, again, it's not always possible, but if you can, you want the solid to be left over because it's really easy to separate solids and liquids. Whereas separating 2 liquids is harder. It's possible, but it's harder. And the same with gases and all that fun stuff. Name one other compound that the student could add to hydrochloric acid to produce zinc chloride. So all you need to do is talk about pretty much anything that has zinc in it. But again, think of your displacement reaction. So Chloride, think about where it is in the reactivity series. The only two that you can kind of think of here is zinc hydroxide would work. You can also put the chemical formula for it, so ZnOH2 if you want. Or you could have said zinc carbonate is the one I was thinking of. Zinc carbonate. And again, that's all to do with your reactivity series and all of that fun stuff that you definitely don't absolutely hate. So for part 4, describe how the student should obtain the crystals of zinc chloride from a solution of zinc chloride. So as you can see here, it's aqueous, which means it's dissolved in the liquid water. So how do you actually extract those crystals? Again, I'm hoping that you've done this experiment in class. If not, I would recommend just looking it up on YouTube, because there are videos online that will have all of that fun stuff there. But essentially what you want to do is you heat up the solution until you hit something called the crystallization point. That's the point where, shockingly, crystals can be formed. So all you want to do is, you can also say, you know what, I'm going to word it a bit more simply, because simplifying the words is a lot better. So all you want to do is heat until crystals form. Okay? So again, the fancy way of saying that is the crystallization point, the point where crystals are formed. Crystallization is the process of forming crystals, but heat until crystals form is perfectly fine. You don't have to use the fancy words all the time. And then all you do is you leave the solution to cool. So the interesting thing about this whole crystallization process is that once you start it, it does just naturally keep going on. So you can just kind of start it and then leave it to run. It's almost like starting a fire, right? You put the energy in to start the fire, and then the fire itself generates more fire. Ionic equations are always a bit tricky. So it tells us here zinc chloride is also produced in a displacement reaction between zinc and copper chloride solution. And it gives us this equation, Zn plus zinc plus copper chloride makes zinc chloride plus copper. Complete the ionic equation, and a lot of students get a bit stuck on these. You can use the periodic table to help you. However, in this case, it's actually not necessary. The only thing you need to remember is that the charges must be balanced. Again, this is something you will learn in physics as well. So in other words, on this side, if I have a 2+, on the other side I must have a 2+. Now, the other letters should be fairly simple, right? We're going to have copper and we're going to have copper, because that is what's going to exchange. Remember, the chloride doesn't change at all. Okay, it's part of the reaction, but it's not actually doing anything. Instead, it's the zinc and the copper that's really reacting. So, on this side we have 2+. The copper will just have no charge at all. So here the zinc must have, the copper must have 2+ as well. That's the easiest way I can explain it, because if there's 2+ on one side, there's 2+ on the other. You can use the periodic table to work it out. For example, let's say it's beryllium, for instance. I know that's going to lose 2 electrons, so it's going to become Be2+. And likewise, oxygen is going to gain 2 electrons, so it'll be O2-. That's probably the easiest way to do it, but again, you can just make sure that the numbers are balanced. In total, there's 2+ on this side, 2+ on this side, it's all balanced, it's all good. So, why is zinc described as being oxidized? Well, if you remember your acronym OIL rig, all that stands for is oxidation is loss of electrons. The of electrons obviously isn't part of it. Reduction is gaining of electrons. So in this case, because as you can see, zinc is becoming a positive ion, it means it must have lost 2 electrons. Because the only way that an atom can become positively charged is by losing electrons. It doesn't really gain positivity, it loses negativity. So, in this case, it's described as being oxidized in the reaction because it loses 2 electrons. Like so. So I hope that makes a bit more sense in terms of those two parts. Here is a little bit of physics. So zinc and copper can be used with another substance to produce electricity. So complete figure 7 to show how zinc, copper and another substance can be used to light a lamp. So we need to label up everything and make sure we put the actual diagram. Now the actual circuit diagram does not have to be that crazy. So if you'd like, we can just continue these two down. And it kind of looks like electrolysis to an extent. So what I want to do is put here my excellent drawing. What is this going to be? It needs to be something called an electrolyte. So it could be water, but it has to have dissolved ions inside of it because we need it to carry a charge. So it could be like, it could even be like a juice drink really. But you could dissolve salt in water to make an electrolyte if you wanted to, something along those lines. And what we're going to do here is we're going to put two cathodes, well, not two cathodes, but the two electrodes, like so. And that's going to be our copper and our zinc. That's all you need in order to actually produce a current. Again, the electrolyte is really the difficult bit here, because a lot of people forget that you're not just submerging it in water, you're submerging it in something that has ions inside it. So you can ionize water by dissolving salt in it, for example, but normal water won't necessarily work. And yep, zinc, copper, boom, all done. Does the order matter? No. Although technically in real life it would, for the purposes of the question, the actual order, so zinc on the left, copper on the right, doesn't make a difference. So in GCSE they're not expecting you to know that copper should be on a certain side and zinc should be on the other side. So if you put copper and then zinc, you'd get the full marks. Here we're talking about groups in the periodic table, and the elements in group 1 become more reactive as they go down, and rubidium is below potassium. So in other words, rubidium should be more reactive than potassium. Cool. In fact, rubidium is it's one where you're going to start not being able to do it in school because it actually explodes. So it goes bang. Not like a massive explosion or anything, but it is more of an explosion, whereas potassium is more of a fizz. So rubidium and potassium are added to water. Predict one observation you would see that shows the rubidium is more reactive. There are loads of different answers, okay? So I'm going to put maybe a couple on here, but we're going to talk through some. So more bubbling, for example. So if it's more reactive, it's going to bubble or fizz more. Another one is that you might get a brighter or bigger flame. So depending on how much you put in, it does actually kind of catch fire. Some others you could say is that rubidium would catch fire more quickly. It moves around faster. So when you put this in there, when it's reacting, it's being pushed around. So rubidium would move around faster. You can say it explodes. So I mentioned that rubidium explodes and potassium doesn't. You could say rubidium will disappear faster. So the reaction will be over a shorter amount of time. You could also say it melts faster or anything like that. Now we have to actually explain why it's more reactive. And this has all to do with our electron shielding and all of that fun stuff. Essentially, if you remember, group 1 elements want to give up 1 electron because it's easier to give up 1 electron than gain 7. So it's easier for them to lose electrons as you go down. Well, think about it. What changes as you go down the periodic table? Well, it's the number of periods. The number of periods is simply the number of shells. So something to do with the number of shells affects how easy or more reactive an element is. So the easier it is for you to lose that electron, the more reactive that element's going to be. And it's because of the shells. And why is that? Well, there's a few reasons. The first one is simply that the outer shell is further away from the nucleus. That's one thing. So because it's further away from the nucleus is positive and the electron is negative, it has less of a hold on it. So it's further away, so there's less electrostatic force between the nucleus and the electron. So it's easier for it to rip away. That's why the opposite is true for group 7 materials. Because as you go down, the number of shells still increase, but they want to gain an electron. So because the outer shell is further away from the nucleus, there's less of a pull from the positive nucleus because it's further away. So that's why there's this inverse. So in group 1, as it goes down, because it's easier to lose an electron, it's more reactive. But because it's harder to gain an electron for group 7, it's less reactive. But that's why there is that kind of discrepancy, that difference. So there's less electrostatic attraction. From the nucleus. And so the electron is more easily lost. And that would be it. And again, the exact opposite would be true for group 7 materials. And you could use the exact same wording, but say, that's why it's harder. So it's harder. So the last sentence is the only one that changes. It's harder to gain that electron. So balancing equation, something that a lot of students really bloody despise. Here's what I would start with, okay? I would start with writing what's actually going to happen, like what are the end products. So with the reaction between rubidium and water, and the same with any group 1 element and water, it's basically a displacement reaction, kinda. So you're going to get rubidium hydroxide, OH. And what are you going to have left over? Well, if I have a look, we've got rubidium OH, but because we're meant to have 2 H's, that means we're going to have also hydrogen over here. Now, that's balanced, right? So are we done? No, because you need to remember that when you have hydrogen, it's diatomic. So that means it always exists in pairs. Always. You don't really get a single hydrogen atom. Okay? So that's hydrogen gas, so H2. It doesn't say for us to use symbol, as in the thing that says whether it's solid, liquid, or gas or anything. So now we need to balance it, because as I can see, there are 2 hydrogens here, there's 3 here. How do I balance equations? Well, what I do is I write each element down, and I say how many. Well, on the left side we've got 1 rubidium, the right side we've got 1, so that is actually all good. Cool. Then I go down and I look at the next one, which is the hydrogens. Here we have 2, here we have 3, no good. So I need to somehow make them the same. So what's the lowest common multiple of 2 and 3? It's 6. So if I put, in fact we could probably make it a bit easier. What we could do is put a 2 in front of here to make that 4 hydrogens. And then because this is H2 and then 1 more H is 3H, we could put a 2 here. So what does that now become? It becomes 4 on the left, 4 on the right. But now our rubidiums are out of order. So what we can do is put a 2 in front of here and we're done. Essentially, it's a game. It's not a very fun game, but you can just kind of write down a table and then keep adding more and more and more to see what you get. Yeah, that's probably the best way to do it, because then we had 2 and then we had to add more. Again, the key thing to look at here is where your hydrogens actually are. So the H2 being 2 hydrogens and then the OH being another hydrogen. So I first said lowest common multiple until I realised, hang on a minute, I can increase it by 1 by just adding a 2 in front of here. It isn't the easiest thing to do in the world, but with practice it does become easy. But all you're doing is you're checking that all the atoms on the left match the ones on the right. It's just a puzzle. It's just a game. Keep practicing it. I promise you, you get there. Here we have a little bit of a multiple choice. So the noble gases are in group 0, or group 8, depending on what you want to call it. Which is a correct statement about the noble gases? Tick one box. The noble gases all have atoms with 8 electrons in the outer shell. I can see why you'd think so, but remember, helium is a noble gas and it only has 2 electrons in its outer shell. Remember, this is actually why we don't normally call it group 8 elements, because there aren't 8 electrons in all the outer shells. It just means that the outer shells are full. And sometimes, well, in the case of helium, that means there's 2. So it's not this one. Noble gases have boiling points that increase going down the group. Maybe, maybe not. The noble gases have molecules with 2 atoms. Well, that's the whole diatomic thing. This is actually not true because they are unreactive, which means they won't form those diatomic bonds because they're not reacting with each other. Noble gases react with metals to form ionic compounds. They don't really react at all, so it must be this one. That is process of elimination, but I would recommend checking as well, does this make sense? The boiling points increase going down the group. Well, if you remember back in question 1, we mentioned about the whole melting and boiling point thing. Generally speaking, as you go down the periodic table, melting and boiling points increase. So this is a true statement. Noble gases, the boiling points increase going down. So here I can already tell what this is going to be. So information about 3 isotopes of neon. Mass number, percentage abundance, calculate the relative atomic mass. Relative atomic mass is the mass number on a lot of periodic tables. Not necessarily the one that you use in school, some of them they aren't, but in a lot of them they are. and we have to give you answers to 3 significant figures. So how do you do this? Well, all you do is, it's kind of like working out a mean from a table, kinda, in the sense that what you do is you take the mass number and you times it by each abundance, okay? And that's the key thing here. So let's quickly do that. So if we say, add a new kind of column to our table, and we're going to just times the percentage abundance with the mass number. And when I say times the percentage abundance, I do mean that we're going to make it, we can leave it as a percentage. So if we do 90.48 times 20, that is completely fine, because we're going to do something a bit cheeky later on. If you want, you can actually divide them all by 100 now. So what would be easier? You know what? I think it might be easier if we just do it separately. So what I'm going to do is get my calculator out. There is a percentage button on your calculator, this yellow one here, shift answer. We can just type in our percentages, 90.48 multiplied by 20, which should give us like 0.18 or something like that. Sorry, 18, yeah, 18.096. And then keep going. So change the percentage to 0.27, whoops, and that is now 21, gives me 0.0567, and then do the very last one, 9.25 times 22, and add them all up, and that is your answer, 2.035. And once you've added them all up, so let's quickly do that. 18 point, that's not a point, 0.096, add 0.0567, that's not a 7, add 2.035, add. That is our relative abundance. It says relative atomic mass to 3SF is 20.2. That is the correct final answer. Now, I know some of you may have teachers who have shown you the question, shown you the method where it's like something like this, where it's 20 times 90.48, add 21 times 0.27, add 22 times 9.25, all over 100. It's the same thing as what I've just done. So I think this makes more sense because it's more similar to what we've done in maths, where you just take the two numbers in the table, multiply them together, but remember this is a percentage, so you're actually doing 90.48%, 0.27%, 9.25%, and adding them up. But if you do it this way, you will get the same answer, I guarantee it. So it is kind of up to you, whatever way makes sense to you, whatever way works for you. So this whole question is about electrolysis, probably one of the hardest topics in chemistry. Molten sodium chloride is electrolyzed in an industrial process to produce sodium, and this is the kind of simplified version. Okay, so they pump out. Yep, wonderful. Which is the correct half equation for production of sodium? Now, half equations do confuse a lot of students, but just remember the charges have to be balanced, and you can use your periodic table to know what the ions should be. So immediately, if I look at this, my charge on the left is -1 from the electron, and it's +1 on the right. Can't be. So the next one, Na to Na plus E minus. Well, the charge on the left is 0. Charge on the right is 0. Could be. I'm not saying it is. I'm saying it could be. Na plus E minus. Well, that's 0 again, and that's 0, so it could be. Then Na plus to, so this is 1 to -1, so it definitely can't be. So now it's a 50-50 shot. Can you see how that would make, I mean, if you knew nothing about electrolysis, that would make your life a bit easier. Now the question is, how does it actually work? Well, you have to decide where the chlorine / the sodium is actually being produced. Now, with sodium, is it going to be a positive or negative ion? Well, if we look here, sodium is in group 1, which means it will form Na plus ions. Now, sadly, we have Na plus ions on both sides. So the question is, in terms of electrolysis, will it take negative charge or will it take positive charge? So in this case, as you can see, the sodium is being split into sodium plus and electrons. In this case, it's sodium plus electrons makes sodium. And in this case, it would be indeed the second one, Na plus electrons neutralizes it and makes it a deionizes it, right? So it stops being an ion. And yeah, that's what you have to do. But again, the trick between doing the whole process of elimination is very useful to just make it a 50-50 shot instead of a 1 in 4. Okay, so meshes used to keep the products of electrolysis apart suggest a reason why they must be kept apart. Now again, this might not be something you've been specifically taught, but you need to, I hate saying this, but you need to think. So, if we look at this half equation, we've split sodium up into positive sodium and electrons. A similar thing would happen to chlorine. However, chlorine would form a negative chlorine ion, for example. So, why do you want to keep those separated by this mesh here? Well, if you think about it, if we have negative chlorine and sodium plus, well, they're really going to want to react because they will neutralize each other. Remember, all atoms and molecules and ions want to be neutral overall. So, simply put, it's to stop them reacting. To stop them reacting to form sodium chloride again. Because the whole point here is we've taken sodium chloride and we've split it into sodium and chlorine. We don't want them to reform it because that kind of defeats the purpose of doing the reaction. And which type of particle passes through the mesh in the electrolysis? It's an atom, electron, ion, or molecule. They are the ions that pass through the mesh. Remember, the products are the Na plus ions and the negative chlorine ions, not the electrons themselves. They actually get used up because they go from one place to another. So they're not technically products, so they're not the ones going through the mesh. We're trying to extract the chlorine and the sodium. Okay, this one's a bit tricky. Aqueous sodium chloride solution is electrolyzed in a different industrial process. 2 gases and an alkaline solution are produced. So, here's where things get a bit tricky. So we have which 2 ions are present in the aqueous sodium chloride in addition to the sodium and the chloride ions? Well, it's an alkaline solution, and what produces the whole alkalineness? It's OH minus, hydroxide ions. And we also going to have some kind of acid being produced. That's produced by H plus ions. So remember, the water itself is going to split into OH minus and H plus. The OH minus makes it alkaline, the H plus makes it acidic. In this case, there just happens to be more OH minus than H plus. And what is the name of the alkaline solution produced? Well, we have sodium chloride being split up, and it's going to react with the OH minus ions to make sodium hydroxide, which, if you'd like, is also NaOH if you if you prefer. And again, how do I know this? Well, sodium, the Na, as we know, makes a +1 ion. Hydroxide is -1. So those will combine together. You won't get, for example, chlorine and OH minus because those are 2 negative ones. You could get hydrogen chloride, HCl, but that is hydrogen chloride, right? It's hydrochloric acid. So it's the acidic product. But in this case, we're looking for the alkaline one, so that's NaOH. If you're ever confused, anything with OH is going to be alkaline. Anything with just H is going to be acidic. So in this case, if they're naming the alkaline solution, you know you're going to have OH in it. So we know that the OH is going to be in it. Well, what's the only thing that will combine with a negative ion? Well, it's going to be Na, because Na is the positive ion. Okay, again, back here, we have Na plus and Cl minus, and back here again, we know that it's Na plus. So hopefully that makes a bit more sense. Now the question is, how the alkaline solution is produced? Oh my goodness. You should refer to the processes at the electrodes. Well, again, 3 marks. Let's put our classic 3 bullet points because we don't want to write anything we don't need to. Simply put, the sodium ions, the Na plus ions, and the hydroxide ions are left, right? They're left behind. Because remember, we're actually producing in this reaction, sodium. So what's going to be left inside the solution is going to be a bit of sodium, but it's also going to be the hydroxide ions. Now, because hydrogen ions are reduced at the, I'm going to write it out actually, negative electrode. Why would that be? Well, remember, hydrogen ions are positive, so they go to the negative side because opposites attract. So you have this negative electrode, you have hydrogen ions, but they're positive, so they want to go to the negative side, in the same way that OH minus will go towards the cathode, the positive side. To produce hydrogen. Perfect. Lastly but not least, the chloride ions are oxidized at the cathode. Actually, oh wait, I just realized we didn't use the word cathode, so we didn't use the word electrode. Let's call it the positive electrode. To form, what did we say? Sodium hydroxide, NaOH. Or, sorry, to form chlorine even. God, what am I talking about? Chlorine. So the alkaline solution is just basically produced of what's left over. So we have the... Maybe I wrote this in the wrong order. The hydrogen ions are used up because they're reduced at the negative electrode to produce hydrogen. The chloride ions are used up because they're at the positive electrode, which means the only thing we have left is sodium and hydroxide. So that's the only thing that can react. That is probably the way I should have written it round. So my apologies for that. Let's move this all up. So again, the hydrogen and chloride ions, which they mentioned back here, in addition to sodium and chloride, those two are used already. The only thing we have left are sodium and hydroxide. This question is about silicon and compounds of silicon. The reactivity series sometimes includes non-metals such as carbon, hydrogen, and silicon. Silicon can be extracted by reducing silicon dioxide with different substances. One reaction is 2 carbon atoms mixed with silicon dioxide makes silicon and 2 carbon monoxide. Explain what this reaction shows about the position of silicon in the reactivity series. Now, whenever you get these kind of equations, it only tells you one thing. If carbon is before silicon or silicon is before carbon. That's it. It doesn't tell you the overall reactivity series. You have to do a bunch of reactions to that. All this tells you is that silicon is less reactive than carbon. So that's what it tells you. But look at the verbiage they've used. Explain. So they haven't said state what this reaction shows. If they said state, we're done. We stated what it is. Silicon is less reactive than carbon. But they say explain. And why? Well, why do I know that? Because carbon displaces silicon. Okay? If it didn't displace, so if no reaction took place, then the reverse would be true. But any atom that displaces another atom is always more reactive. So carbon is more reactive than silicon because it displaces silicon. So, aluminium also reduces silicon dioxide. Carbon is used rather than aluminium to reduce silicon dioxide because carbon is cheaper. Carbon can be obtained by heating coal. Aluminium is obtained from aluminium oxide. So why is aluminium more expensive? Aluminium is actually, honestly, it's actually a really fascinating metal because it didn't really exist until the Industrial Revolution. And that's not because it literally didn't exist, it's because we had no way of refining it. Because unlike normal metals, so most metals like iron and copper and nickel and steel and etc., you can displace those just with carbon by heating them up with coal. However, aluminium is less reactive than carbon, which means it cannot be it's more reactive than carbon, so it can't be displaced by carbon. Which means, until the Industrial Revolution, we couldn't use aluminium at all. And it's one of the few metals that, well, it's not one of the few metals, but it's one of the major metals that we couldn't use, which is really fascinating in my opinion, but I'm also a nerd. The only way you can actually extract aluminium from its ore, aluminium oxide, is through electrolysis, which is an expensive process. That's why. So simply more energy is needed to produce aluminium, which is why it's more expensive. Simply put, because aluminium obtained by electrolysis instead. Really interesting, but that's why it didn't really, wasn't present in the world in that sense. Pure aluminium. It was only existed as bauxite, as its ore. And it gives us magnesium as well. So, magnesium also reduces silicon dioxide. The reaction is 2 magnesium atoms and silicon dioxide makes silicon and 2 magnesium oxides. Give one reason why the products are difficult to separate if magnesium is used to reduce silicon dioxide. So, what makes products difficult to separate? It's only really one thing. It's what state they're in. Generally speaking, it's easier to separate two things that are different states. So a liquid and a gas, easy to separate. Solid and a gas, easy to separate. Solid and a liquid, easy to separate. But when they're the same state, it becomes very difficult. So for example, two liquids separating them can be really tricky. Two gases, really tricky. Two solids, really tricky. So simply put, both products are solid. And again, that is the products are solid. That is really the only consideration that we care about when it comes to separating our products. Because again, if it's mixed with a liquid, all we have to do is filter it. That's quite easy. But if they're two liquids, for example, we have to use depending on if their densities are really different, maybe they'll separate normally. But generally speaking, we might have to use a centrifuge. If these are both solids, you're going to get two powders that are mixed together. How do you separate that? Pretty tricky. So, calculate the minimum mass in grams of magnesium needed to completely reduce 1.2 kilograms of silicon dioxide. So what we need to do here is use the atomic masses and the molecular masses in order to work this out. Sorry about that, I had something in my eye I had to get out. So, we have the atomic masses. We need to also work out the molecular mass, and in this case of silicon dioxide. So SiO2, if we're looking for the molecular mass, that would be, well, how many silicon atoms are there? There are 20. Sorry. There's one silicon atom and it weighs 28. How many oxygen atoms there are? There are 2 and they each weigh 16. So plus. So that would be 32 plus 28 is 60. So 60 atomic mass units. Perfect. Now, when we do these units, we actually do them in terms of grams. So what we need to do first is change 1.2 kilograms into grams, which is 1200 grams. Perfect. Now, if we want to work out the number of moles, so number of moles of SiO2, all you do is you take the mass that you're looking at and you divide it by the relative atomic mass of, the molecular mass, okay? So again, this has to be in grams. Just keep that in mind. So knock off a 0. That should be 20 moles. Perfect. Now, going back to the equation, if you look here, we have 20 moles of silicon dioxide, but we have 2 mg. That means we need 40 moles of Mg, because for every 1 mole of silicon dioxide, there is 2, that's why the number 2 is in front, 2 moles of magnesium. So if we have 20 moles of silicon dioxide, we need to have 40 moles of magnesium to fully react. So number of moles of Mg is equal to 2 times 20 equals 40. And again, the reason why we do that is because there's a 2 in front. If there's a 3 in front, it'd be 60. If there's a 5 in front, it'd be 100. If there was 2 in front of the SiO2, we would half this one, etc. So, now we need to go back to the mass. So the mass of Mg, all you do is you take the number of moles, which is 40, and you times it by its molecular mass, or in this case atomic mass, because it's just an atom. Times it by 10 would be 240, double it 480, 960 grams. 5 marks. That is probably a hard calculation. That's where calculations really start getting tricky in terms of chemistry. But again, just to go over the method, you work out the molecular mass to work out how many moles of silicon you need, which means you can work out how many moles of magnesium you need, and then work out the mass from there. Cool. We have a covalent compound, so that's disilicon hexa. Anyways, never mind. And it shows the outer shell electrons, and we need to complete the figure. There you go. Anyways, so how many electrons should silicon have in its outer shell? It's in group 1, 2, 3, 4. So it has 4 electrons in its outer shell, which means there's going to be 2 that are shared between these two guys. So boom and boom. And then what it's going to do is it's going to share 1 with each hydrogen. Why is it only 1? Because hydrogen is in group 1 over here. So, yeah, okay, so it's going to share 1 with hydrogen. But then don't forget, it's gaining 1 from that hydrogen as well. So there's also going to be a dot. You have to use a dot and cross diagram so you can see that the dots are the electrons the hydrogens are providing, and the crosses are the ones that the silicones are providing. Wonderful. Now we have a pretty beefy equation, Jesus Christ. And it tells me that 30 centimeters cubed of this compound is reacted with 150 centimeters cubed, an excess, of oxygen. Calculate the total volume of gases present after the reaction. All volumes of gases are measured in the same temperature and pressure. So, here we're once again using the equation to help us out here. And there's quite a few numbers. Calculate the total volume of gases present after the reactions over here. Okay. So first of all, it tells me it's 30 centimeters cubed of this with 150 centimeters cubed of this. What would it produce? Well, the problem is this, it's an excess. So this number is not really the one we want, because that's an excess. It means that on this other side, there's actually going to be a bunch of oxygen left over. So we need to get rid of that oxygen. So I need to work out how much I would actually need before I do this. And the way we do this is work out how many times more. So again, it's the ratio thing we used before, right? So it's 7 and 2. So if I do 7 divided by 2, there should be 3.5 times more oxygen than SiH6. Si2H6, jeez, okay? So, all I do is I do the volume of oxygen I actually need is going to be 30 times 3.5, which is 105 centimeters cubed. So what's the excess? So the volume of the excess, so what's going to be left over? Well, it's going to be 150 minus 105 is 45 cubic centimeters left over. Cool. Again, we're trying to look for all of this at the end. With the volume of water vapor, well, because don't forget, this excess is going to be added on to the end because there is some more O2 over here. So we do have to add that on at the end. So now let's do the H2O. So we've worked out the volume of this mystery stuff over here, this oxygen. Now I'm going to do the H2O and then I'll probably do the Si stuff. Again, if we look at how much bigger it is, it goes from 2 to 6. What's 6 divided by 2? It's 3 times as much, so that's 3 times 30. So that's going to be 90 centimeters cubed. And lastly, oh no, that's a solid, so we don't need to do it. Yeah. So again, the gas is present. It's not just water vapor. There's an excess of oxygen. So the gases is just going to be 90 plus 45, which is 135. So I hope that makes sense. If we're looking at just the gases present afterwards, it's water vapor and oxygen. So the oxygen one we had to add on because it tells me there's an excess of oxygen, which means not all of the oxygen will react. Then we just have to work out how much that would be. Yeah, so hopefully that makes a wee bit more sense. That's the end of question 7. So, 8.1. Question about acids and alkalis. The final question in the paper. Explain why the pH depends on the strength of the acid and the concentration of the acid. Well, 1, 2, 3, 4. Classic, right? Classic, 4 bullet points. So, what's the general principle? Well, the general principle is that the pH depends on, so the pH depends on H plus ion concentration. Remember, we don't really talk about the number of H plus ions because that depends on how much liquid that we have, right? So instead we talk about the concentration, the amount per unit volume. So it's more but in the same space. So in general, pH depends on the H plus concentration. If you want to justify this, more H plus, less pH. Simply put. And now we can go here. So the strength of the acid, the stronger the acid, the greater the ionization. So that means it's producing more H plus ions. Hence lower pH. Because essentially it's ripping off H plus ions more frequently or in a greater quantity. Let's move this bullet point down just so we can have a little bit of separation here. I actually only need one more point because this and this actually count as 2 marks. And lastly, higher concentration, higher concentration, the more acid per volume, hence lower pH. And that's all you basically have to write. Yeah. Anyways, a student titrated 25 cubic centimeters of hydrochloric acid with 0.1 moles per decimeter cubed barium hydroxide solution. How cool does that sound? Volume used, yeah. Student calculated the volume of barium hydroxide to be used in the real titration calculation to be 23.5. But how? Simple. First of all, he would calculate an average. But there is one thing. So he calculated the mean. However, he didn't use all the values. If he used all the values, then it would be skewed closer to 23.9. But if you notice, this is an anomaly, which makes sense because it's the first time he did it. He probably just made a little bit of a mistake, which is normal. You get better at things as you do them more. So the mean of number 2 to 5, because 23.90 is an anomaly. So simple. It was an anomalous result, so we disregarded that and calculated the mean of the other 4 numbers. So here we have to work out the concentration of HCl in moles per decimeter cubed. The problem is our volumes are in centimeters cubed. Remember, to go from centimeters to decimeters, you're dividing by 10, but since it's cubed, you're dividing by 10 cubed, which is the same as 1,000. So first of all, I want to work out the moles of barium hydroxide. Moles of barium OH2, which is simply going to be 23.5 is the number they have. Convert it into decimeters by dividing by 1,000. So again, that's in centimeters cubed, but our concentration is in decimeters. So divide by 1,000 and then times by the concentration. So remember, when you do volume, in general, the concentration is equal to moles over volume. So if you want moles, you're doing concentration multiplied by volume. It's just that I've converted my volume into decimeters because you need to make sure the values are the same, which is going to be 23.5 over, it's going to be a tiny number, isn't it? Let's use standard form, why not? Standard form is probably very useful for this. Moles, perfect. We also want to work out the moles of HCl. We do the exact same calculation, but instead of using the HCl one, because we have 25 cubic centimeters, but we need to change that into... hang on, no, actually, because we don't have the concentration. Never mind, I'm being stupid. So don't forget, the barium hydroxide is 2.35, but this is 2 times that. So we just times this by 2, which would give us 4.7 times 10 to the minus 3. Because again, you're multiplying by 2 because there's a big 2 in front of the HCl. Perfect. Hydrochloric acid in moles per decimeter. Okay, now all we need to do is divide it by the volume. Yeah, we just need to divide it by the volume. So all we need to do for the concentration is the moles, which is 4.7 times 10 to the minus 3, over volume. But don't forget, our volume is in centimeters cubed. So we need to do 25 divided by 1,000, which is 0.025. So 1, 2, 3. And that'll give us our final answer. So let's times up by 2 to get our 4.7, blah, blah, blah. Divide it by 0.025. So it'd be 4 times 40 basically. We get 0.188 moles per decimeter cubed. So again, the tricky part here is definitely making sure that you have the right units, that you've converted them into decimeters. You could technically convert these into centimeters, but that's a bit harder. Another student titrated sulfuric acid with barium hydroxide solution. The equation is bleh, all that stuff. Student measured the electrical conductivity of the mixture during the titration. The better a conductor, the higher the electrical conductivity. So it starts off really high and it goes lower and lower and lower as this titration was added. We need to explain why the electrical conductivity was 0 when the sulfuric acid had been neutralized. Well, it says use the equation for the reaction. So here, the key thing is, as we're titrating it, we're neutralizing the reaction. That means that the ions inside the mixture are binding with opposite ions, which means it's being... I mean, that's what neutralize means, right? You have OH minus ions plus H plus ions producing water, which is completely neutral. Remember what we said earlier in the paper. There needs to be some kind of charge carriers for electricity to be able to pass through it. So simply put, there are no ions free to move. Ions. Cool. And the reason why is, again, if we look back here, you could also say that this is insoluble, actually. That's a really good one. Because BaSO4 is solid, basically. It's a solid. Electrons won't be able to pass through it, or charge won't be able to. And also, the hydroxide ions have reacted with H plus ions to produce water. So that's simply the reason why. So all of the ions are gone. We no longer have anything dissolved in the water, or in this case, in the water, because barium's BaSO4 is a solid, which means it's insoluble, which means it hasn't dissolved, which means there are no ions from that. But also, the OH minus ions and the hydrogen ions have reacted and neutralized each other, which means there are no ions left to actually create an electrical current. And lastly, the student added a further 10 centimeters cubed of barium hydroxide, and the electrical conductivity increased. Why? Well, the barium hydroxide, this was aqueous. It can dissolve, which means there are now ions free to move. So simply put, the mixture now has... What on earth just happened there? The mixture now has ions free to move. And that's it for that paper. So again, I will consider doing the physics one, assuming that this one and the biology one do relatively well, so there's some kind of demand for it. But other than that, I hope that was useful, and I hope you have a really good day.